Hi, everyone. Today we're going to show how we accelerate Spark on Azure with the new hardware offloads that are going to be introduced into the Azure cloud. My name is Yuval Degani. I work for Mellanox Technologies. This is Evan Bernes from Microsoft Azure. Just a few words about Mellanox. So Mellanox is an end-to-end designer and supplier of interconnect solution that goes for network adapters, switches, systems on a chip, cables, silicon, and software. Anywhere between 10 and 400 gigabit per second for Ethernet and InfiniBand fabrics.
Yeah, so Microsoft Azure is the only RDMA-capable major cloud provider out there, and we've done this in partnership with Mellanox over many years. You can find InfiniBand fabric technology on our H-series VMs, which are CPUs connected by FDR InfiniBand, as well as our NC-series VMs, which are GPU-accelerated VMs, also powered by FDR InfiniBand. We see dozens of different use cases across a wide variety of verticals from academia, industry, government, and beyond. And we have clusters all over the world today. And this is a really exciting opportunity for us to launch this new capability, Spark RDMA, on Azure.
All right, so why are we here? So Azure Hardware Accelerated Networks will soon support general purpose RDMA, meaning you can use any kind of RDMA application on top of your Azure VMs. And this is going to be on top of SRIOV. We're soon going to explain all those fancy words. And the second thing is that Spark RDMA Shuffle plugin, which was presented in the last Spark Summit in Dublin, can now be used in the cloud. So you no longer have to have your own specialized hardware for enjoying these hardware offloads. You can just run them on the cloud and have instant speedups with the hardware that is already there. So what's RDMA? RDMA stands for Remote Direct Memory Access. It basically lets you read and write from and to remote memory from your local machine. It gives you 0 copies since you're doing transfers directly from memory addresses, either remotely or locally. And it basically gives you direct hardware interface bypassing the kernel and the OS, TCP stack, and everything within the I/O path. We can see here in this diagram how a buffer starts in this kind of Java application. Once the connection is being established, any kind of communications being done on sockets will have to go through the kernel on each operation in the data path. Doing a context switch to the kernel, going through the stack for sockets, TCP IP, driver, and only then you get to the actual NIC that you're trying to use. Now in the RDMA case, you basically, once you establish a connection and you have everything set up, it basically lets you access the hardware directly. You just write stuff to memory from user mode code, and this is all you have to do. You don't have to go through all this stack. So it cuts down on CPU significantly. Other than that, so RDMA basically implements flow control and reliability offloaded in the hardware. It gives you sub-microsecond latency, and it's basically supported in almost all mid-range to high-end network adapters. Most probably your servers support it, the ones that you're already using today.
Yeah, so one of the reasons why we decided at Microsoft that it was really important to bring this capability to the cloud is we're big believers in the field of high-performance computing. So we started doing this actually many years ago. And we did this because we had customers from the automotive industry, oil and gas, the research academic community coming to us and saying the power of the cloud is really compelling because we give them a very flexible, agile way to run these kinds of at-scale workloads. So we really have tried to differentiate what we do on Azure versus what is available in other clouds through this RDMA capability through InfiniBand. And so we offer the lowest latency fabric of any cloud provider out there. And we provide pre-built OS images, so anyone can just go on, grab something from the Azure Software Marketplace, bring it down, and have virtual machines up and running using RDMA in just a matter of seconds. And like I mentioned earlier, we have a broad fleet of GPUs that can use this, which is really key, obviously, for an audience like yourselves, where AI is obviously at the core of everything you all are thinking about now. And as you can see here, we really try to have the broadest support for data analytics and AI frameworks out there.
All right, so how is this all working? How do you get general purpose RDMA available in the cloud for the first time in any major cloud provider? So Azure Accelerated Networking is basically built on top of SRIOV, which is, it stands for Single Root Input-Output Virtualization, basically meaning that you get a virtual physical device on the VM. What that means is it's not a software emulated virtual network adapter. It's a virtual network adapter that works directly on top of a physical device. So it's basically an extension or a virtual extension of the physical device exposed directly into the VM. We can see on both sides here, so on the left-hand side, this is without accelerated networking, and we see that all of the traffic from the VMs has to go through the virtual switch that is on the hypervisor, meaning that every piece of network traffic that is going back and forth on the fabric has to go through a bunch of stacks of software also on the VM and then on the host on both directions. Whereas in the accelerated networking on the right-hand side, we can see that we basically expose a fraction of the network adapter directly to the VM, allowing direct access to the physical NIC from the VM. So before we dive in on what we are actually doing here for Spark, I first want to go into how the shuffle internals work in Spark. And then we'll understand how we do the acceleration here in the context of RDMA on Azure. So shuffle basics in Spark. So this is standard Spark. And as we know, every shuffle phase consists of a map and reduce phase. Usually, the map phase starts with input coming from some kind of persistent storage, most commonly HDFS. Now, this data comes into the map task, and the first step that will be in the map task is to partition the data. In this case, we basically take all of the data that's coming in and group it by the partition. In this case, we have the blue partition, the purple partition, and we basically end up with the map output that basically sorts the partitions and groups them by this specific partition in a continuous buffer. Now, once the map output is ready, the next step is to write the map output into a file, and this happens on each map task. Once we have those map outputs written, then a map output status is being created, which basically describes where the blocks are located. The map statuses are then being transmitted into the driver, the master in this case, that basically holds and bookkeeps all this information so that further reducers will then be able to fetch the appropriate blocks that they're looking for. And this is where the reduce phase begins. So we basically end up with a reduce task pair partition. In this case, we have a blue reduce task, a purple one, and so on. The first step will be to fetch all of the data that we're trying to process here for that specific partition. And in this case, we basically fetch all of the blue chunks and the purple chunks to the appropriate tasks and so on. Once the data starts coming in, this is where the actual compute job or reduce task can start. So diving in a little more on how fetching the blocks actually works. So this is the standard shuffle read protocol that exists today in every version of Spark starting 1.6. And basically, everything starts with a reader, which is actually a reducer, trying to fetch the appropriate blocks for that specific partition it's trying to process. The first step will be to request the map statuses from the driver that the driver is bookkeeping until the end of this shuffle phase. the driver will send back the map statuses, and then the reader will group the block locations it received from the driver by the writer. Then the reader will go through all of the writers that it needs to fetch data from, and will request the blocks from the writers. This will basically cause the writer to locate the blocks, set up a stream of blocks, so then the reader will be able to fetch those blocks from the stream one by one. And this is where steps 6 and 7 repeats themselves until all of the blocks come in, and this is where the actual compute job can begin. Now, as we can see here, specifically in steps 6 and 7, we have RPC messages going back and forth for every piece of block, like every piece of the data. And it can easily be 4 kilobytes, for example, which makes the entire process very inefficient. And this is where we thought that we can do better with the aid of RDMA. So to summarize, the cost of shuffling is basically, shuffling is very expensive. This goes for CPU, RAM, disk, and network IOs. We often see Spark users trying to avoid shuffles as much as they can, just so they don't have to go through these complex operations, which can take a long time to tune and to find the sweet spot on the batch size and so on. And this is where we think that speedy shuffles can relieve developers of such concerns and basically let them simplify applications and focus on the actual job at hand. And this is where the Spark RDMA Shuffle plugin comes in, and this is basically how we accelerate Shuffle in Spark with RDMA. So Spark RDMA is an open source project. There's a dedicated session which I presented in the last Spark Summit, so you can see a more deep dive on the actual technical details and how we do stuff within this plugin. So as I said, it's an open source plugin, free to use, available on GitHub, where we maintain and publish new versions and bug fixes and so on. There's ongoing discussions there, guides on how to deploy, how to tune, and so on. It supports any RDMA-capable device. That goes for Ethernet with the Rocky, which is RDMA over converged Ethernet, and also InfiniBand, used in this case in Azure. So a few design notes about Spark RDMA. What we had in mind, basically, is to have the entire shuffle-related communication done with RDMA. This goes for RPC messaging for the metadata transfer, the map statuses, and of course, the block transfers themselves. Spark RDMA is an independent plugin. It implements the Shuffle Manager interface, which is already built into Spark. It doesn't require any changes to the Spark code, so you can basically use it with whatever existing version of Spark you might have. We support any version 2.0 and up. And you can see on the diagram on the side, this is basically an existing Spark version where we just replace the specific component for the Shuffle Manager. So it reuses Spark facilities, and we do that in order to maximize reliability and to minimize the impact that this plugin can have on the data that is working in production environments. It has no functionality loss of any kind, so it supports compression, spilling, recovery from failed and map and reduce tasks, and encryption and so on, and whatever you used to be working with when you do shuffles. So before we dive in on how we actually do the protocol for the read part in Spark with RDMA, let's have a look again on how the standard protocol works. So as we've seen before, there's a lot of RPCs going on the second part, but the first part, basically stages 1, 2, and 3, are just fetching the map status data from the driver. Now this part stays mainly the same in the RDMA case, but the part where we actually retrieve the blocks is where everything changes. So the only thing that we change in this part where we fetch the map statuses is that we piggyback the memory addresses of the blocks on the map statuses that are already in there in Spark. This basically lets us, once we start fetching the blocks, just giving us the ability to just do RDMA read directly from the remote machines because we already have the memory addresses. In this case, when we do a remote RDMA read, it basically a no-op on the writer side. Because we already have the remote address, we can just read from it, and RDMA reads are operations which are entirely offloaded by the hardware. In this case, it basically removes all of the computations or software stages that has to go through the writer once we fetch data. And this is where the data starts coming in, and we can continue with the computation phase. So zooming out a little bit and comparing the two only on the specific parts which are different. So this is the standard in the RDMA protocol, just cutting out the places where we actually fetch the blocks, which are different. And we can see here, so on the server side, which is actually the writer side, we see that we have 0 CPU in the RDMA case. There's no software, any code and software running in the actual reduce phase. Something even more interesting is the fact that since Shuffle is very memory intensive and CPU intensive, it tends to create a lot of buffers that are floating around and a lot of memory that has to be handled and freed and so on. It usually and most commonly creates overhead in garbage collection, and we can easily see cases where we lose parallelism significantly because of the fact that you have many readers in the network which are trying to fetch blocks from a remote writer, which is now going through garbage collection. Now you have those readers blocked, and they can't process any more data or progress in the computation. In the RDMA case, since we don't have any blocking operations on the writer side, everything is done in hardware, then it can continue to do whatever it wants to, either garbage collection, processing, and so on, without having any influence on the reader, which is trying to fetch the blocks. So on the client side, we basically get instant transfers. We don't get blocked on remote processes. We have reduced messaging, basically no RPCs going at all for fetching the blocks, only for fetching the map statuses. And it basically gives us direct unblocked access to the remote blocks. So to summarize the benefits that we get here, we have substantial improvements in block transfer times, and that goes for latency and the total transfer time of the job. We have improved memory consumption and management because there are 0 copy, a lot less buffers used for RPCs and so on, reducing even more the garbage collection overhead on the job. And we can easily see that in CPU utilization. We basically free up cycles that now can be used for the actual job at hand, the actual computation we're trying to do. It's very easy to deploy and configure. It's packed into a single jar file. You can just couple it with your own Spark installation and so on. And the plugin is enabled through a very simple configuration handle, which we're soon going to see. And it allows finer tuning with a set of configuration handles for users who are very performance enthusiastic and would like to invest even more to find the best possible way to use this. Configuration and deployment are on a per job basis. Basically, it can be deployed incrementally, which is very important when you introduce these kind of things into production environments. Basically, if you have many jobs, you can just choose one of them and have it working with this Spark RDMA plugin while all the other jobs keeps working on the standard Spark way of shuffling data. Okay, so we got to the interesting part. So our demo test bed, in terms of hardware, we have 8 Azure H16 MR VM instances with Intel Haswell CPU. They also have Mellanox InfiniBand FDR adapters running at 56 gigabit per second, 224 gigs of RAM, 2 terabyte of SSD for their working directories. For their workload, what we see here is an high bench TerraSort, which is very popular in the MapReduce and Spark world. And in this case, we use size, what they call gigantic, which is 320 gigs. running on Ubuntu, Hadoop 2.7 for HDFS without replications, just so we can isolate the storage part from this test. This is Spark 2.2 with 1 master, 7 workers, and a total of 112 cores. So in this video, we can see this is just the plain configuration file for HighBench, and this is just the HighBench we can get on GitHub without any changes whatsoever. And this is now running on plain Spark without any changes, without the Spark RDMA plugin. We'll fast forward through the test because it takes about 11 minutes to run, and we'll take a peek at the results. So we can see here that the total runtime for this test case is 685 seconds. Now, let's do the same thing with RDMA. The only thing that we need to change here is to uncomment the line that says which shuffle manager should be used. In this case, the RDMA shuffle manager. It just overrides the default shuffle engine in Spark. And we just run the same test again. This is, again, HighBench without any changes. So we'll fast forward through the test and take a look at the results. So as we can see here, we started with 685 seconds, and we ended up with 262 seconds only by changing the shuffle engine in Spark. To summarize, in this TerraSort case, the performance results we see up to a 2.6x speed up for RDMA, which is very significant, and this is the total runtime of the entire job. It's not only the shuffle phase. If we dive in a little deeper and look specifically on the shuffle phase, we can see here at the top we have the standard case, and at the bottom the RDMA case. We can see that the specific phase on the reduced phase where the data is being shuffled is where we get a 4.4x speed up in that specific phase. Taking a closer look on the stats for the reduced jobs themselves, so we can see that in the standard case, the total runtime, the median is 3 seconds. Out of it, 2 seconds is just for fetching the shuffle blocks. Now in RDMA, the total runtime is just 0.7 seconds, where we spend only 2 milliseconds on fetching the blocks, which basically gives us a 1,000-factor faster transfers. Taking a look on how the shuffle tasks themselves look like in terms of what kind of where time is being spent on the job. So we can see here in orange on the standard Spark case that we spend a significant amount on just reading the shuffle data. Whereas in the RDMA case, we don't see any of those orange bars, basically meaning that read time is actually 0.
So thanks, Yuval. So this is really, like I said, a super exciting announcement for us on the Azure side, bringing SRIOV to Azure. It does a couple of really big things. The first is exactly what Yuval's been talking to you all about today, which is it enables us to bring Spark RDMA natively to Microsoft Azure for everyone here and anywhere else to come and go use whenever they want, however they want. And then the second piece is it enables even more RDMA scenarios than we supported before. So that's really critical for us in terms of supporting the broader RDMA, MPI, HPC, and AI community. And like we said, we'll support literally any flavor of MPI on top of Microsoft Azure. So we're really making headway into presenting a cloud to this at-scale computing community that looks and feels and performs just like the bare metal infrastructure they themselves can get their hands on. And then the last thing I would say, without saying really any more details than this, is we may have a few more announcements about new exciting things we're doing with the H-Series at the Supercomputing 2018 conference, and Yuval and I will be there, and we hope to see some of you there as well.
Thank you.
So I think we have a little bit of time for questions. All right, thanks. So 2 questions, one for Azure and one for
the other one. So so the current, you are already giving this right now in Azure, or do we need to request for it? That's first question. The second question is, just Azure, or let's say if we want to do it for on-prem, do you guys support?
So basically, Spark RDMA is designed to run on any kind of hardware that supports RDMA. So it could be on-prem, it could be on the cloud, in this case on Azure, which is the only large-scale provider that supports RDMA.
And yes, we do support RDMA on Azure today.
Is there another question?
Hi, this is Kevin from Samsung. This is great work, thanks. So I'm aware that IBM has an open source project called Creo that is also work on Shuffle plugin for Spark, which is RDMA supported. So I was wondering, this Spark RDMA work, how is it related to Creo, and how was the difference between the two? Yeah.
Sure. So I'm actually a committer on Creo, so Creo is very close to me as well. But these projects, they have nothing in common except the underlying library for RDMA that they are using, which is what we call Disney. Creo is more kind of an holistic solution that utilizes RDMA. It's basically a storage platform that one of its benefits that it also gives up plugins which you can use in this case for accelerating shuffle as well. Spark RDMA is a little different. It tries to solve a smaller problem without having to have many dependencies in terms of installing and so on. You can just use it as a standalone plugin with your own Spark installation without having to change your entire runtime environment and so on. My point is, Creo is a great product, but Creo is more kind of a general solution for accelerating storage, and this is a more specific solution for accelerating Shuffle and Spark.
Cool. Any other questions?
You say you can configure usage of RDMA at the job level. I suspect you actually mean at the application level?
Yes, so actually for just replacing the Shuffle Manager in Spark, all you have to do is just add those configuration line either within the app or with an outside configuration file. That just basically instructs Spark to use another Shuffle Manager, and this is the RDMA Shuffle Manager. You do have to have RDMA supported in the hardware.
But you're making that configuration change at the granularity of the Spark context then, right?
Yes.
So that's at the application level, not the job level.
Yes, correct.
Just a quick question. Would this work with the external Shuffle service?
So actually, Spark RDMA doesn't support the external Shuffle service. We are looking into doing something like that, but currently it's just a regular Shuffle engine, the default Shuffle engine.
Any other questions? All right, let's thank the speakers one more time. You guys.